Today we are going to learn about irreducibility of polynomials in the ring of polynomials, one of the most important topics in the ring of polynomials. And to learn in detail, first of all, we start with taking an example of a polynomial. And suppose that let fx is x square plus 1, and this polynomial can be considered in the ring Rx. This is a ring of all polynomials over reals. Now in 11 or class 12 we have learned that this polynomial cannot be factorized over R, but can be factorized over the complex. So we claim that fx is irreducible in Rx. So to confirm this one, suppose that if fx equal to x square plus 1 were reducible. Reducible means not irreducible in Rx, then there would exist real numbers a, b, c, d such that this polynomial x square plus 1 can be written as the product of two polynomials of the form x plus b and cx plus d. Its degree is 2, its degree 1, and its degree is also 1. Now from this we have x square plus 1 equal to, if we multiply these two polynomials, then we get acx square plus axd and bcx, so we get ad plus bcx, and plus the constant term will be bd. So this implies on the left we have x square plus 1, and on the right so let us now by equality of two polynomials, we get that on the left coefficient of x square is 1, and on the right coefficient of x square is ac, so these two coefficients will be equal. So we get, so from the equality of two polynomials we have AC equal to 1. Now AD plus BC is the coefficient of x square on the right, and on the left coefficient of x is 0 because the term x is missing over here. So coefficient of x is 0 on the left, so AD plus BC will be 0. AD plus BC will be 0. Now we take the constant terms. On the right it is BD, on the left it is 1, so it will be BD is equal to 1. Now because we have chosen the opposite thing, that we started with if this polynomial were reducible in Rx, so we have to arrive at a contradiction. So for that we start with the number 1, and 1 can be written as 1 into 1, and for this one we put AC, and for this one we put BD. Now you can write from here AD into BC, because R is commutative. R is commutative ring, or we find 1 equal to, now here is a relation, AD plus BC equal to 0. Now we left AD as it is, and for BC we put minus AD, so we get minus AD whole square, or AD whole square is equal to minus 1. This is not possible in R, because the left hand side is 0 or positive, but the right hand side is minus 1. This is not possible. So not possible. So our claim was right, that fx, the polynomial x square plus 1, is irreducible in Rx. Now we consider the polynomial in Cx, where C is the ring of all complex numbers. So we can write this polynomial here. Fx can be written as this one, x square minus minus 1. You can write this one, and x square minus minus 1, and it is I square, since I square is minus 1. And now using this formula, I square minus b square, so it will be x plus I times x minus I. And this polynomial is in Cx, this polynomial is also in Cx, so fx is factorized. So the conclusion is that fx is not irreducible in Cx. Fx is not irreducible in Cx, or you can say that this polynomial is reducible in Cx, or factorized in Cx. Now our main problem here arises whether this polynomial x plus I is irreducible or not. Irreducible or not. So we are going to find the solution of this problem, and this can be considered as the polynomial of the type f(x) equal to ax plus b, where a is 1 here and b is I. We recall C is the field of all complex numbers. So now we are going to set a problem, and if we can solve this problem, then we can immediately say that whether this polynomial is irreducible or not. To do this, so let us consider this problem. Here is a field. So in general, we take a field. Let f be a field. Then fx equal to x plus b is in fx, and where a is not equal to 0, then this polynomial will be irreducible. So we have to prove this, and if we can prove this result, then immediately we say that this polynomial is irreducible in Cx. So proof. Suppose that fx is the product of two polynomials gx and hx, where gx and hx are in fx. Then we have degree of this polynomial is 1. So degree of gx hx is degree of fx, and degree of fx is degree of x plus b, and it is 1. And this one can be written as degree of, or degree of gx, degree of gx plus degree of hx is 1. Here we remember that f is a field, so it is an integral domain. And so this holds. Now degree of gx plus degree of hx is 1. So this is possible only when either this is 1 and this is 0, or this one 0 and this one 1. So we assume that. So we assume that degree of gx is 0 and degree of hx is 1. Then degree of gx equal to 0 implies this is a non-zero constant polynomial. Gx is a non-zero constant polynomial. Constant polynomial. So let So let gx equal to c. C is a non-zero constant in the field F. A non-zero constant in the field F, and so this implies gx is a unit, is a unit. Since we know that in a field every non-zero element has multiplicity inverse, that is every non-zero element is a unit. Here gx is a constant which is non-zero constant, and so gx is a unit. Thus fx equal to x plus b is irreducible in fx. If we consider the other case, that is if degree of gx is 1 and degree of hx is 0, then similarly proceeding with the degree of hx, we can show that hx will be a unit, and in that case too we can say that fx equal to x plus b is irreducible in fx, because in the definition of irreducible element we know that p is irreducible if p is the product of ab, where a and b are in fx. Then p will be reducible if either a is a unit or b is a unit. So here we have seen the same thing as the definition says.